So, we are working on the classical eigensolver problem where we have got a 2-degree freedom system like this. We will continue with the lecture 16 on dynamics of ocean structures module 1 under NPTEL IIT Madras Braces. In the first module we are attempting to discuss the fundamentals of structural dynamics, where we will also give you some design guidelines and how the form based design can be used as a successful application with dynamics as the background. In various examples we have already illustrated that fundamental structural mechanics can be used as a tool to compute some essential characteristics of dynamics given system. Spring mass system is a very elementary example available for demonstration or modeling any multi-degree freedom system. We picked up a 2-degree freedom system model in the last class. We wrote the equation of motion. We solved the classical eigensolver using a classical theory and found out the natural frequencies omega 1 and omega 2 as the values as indicated here, and we already have also derived the stiffness matrix for the columns as EI by h cube, 24 EI by h cube. We know that how they have been derived from the first principles. So, we also identified from the given set of frequencies and mode shapes how to identify the fundamental frequency and the corresponding mode shape. It is a pair, you cannot separate this. It means the mode shape of this has no association with this frequency and vice versa. For example, this mode shape has no association with this frequency. So, every frequency has got a very corresponding unique mode shape, therefore, they are paired, you cannot decouple them. And we also said in the last lecture that mode shape is nothing but the relative displacement of the mass points where you have measured your degrees of freedom. In the last examples we also illustrated to you that if you do not mark the degrees of freedom at the points where the mass matrix is or the mass is lumped, what will happen to the mass matrix, we demonstrated. Therefore, in this example classically every designer used to always lump the mass at a point where the degrees of freedom are marked. Essentially the reason is not to make the mathematics simple, but you are always interested in knowing the structural acceleration or the displacement of the mass point. In all structural system, in any mathematical model, you are interested to know either the acceleration or the displacement at the point where the mass is lumped. You are not interested in knowing at the space point where the mass is not lumped, because we are always bothered as a designer what would be the maximum acceleration given to the floor or the mass. That is why obviously in all mathematical models the degrees of freedom are generally marked at the point where the mass is said to be lumped. That is the reason why we do so. But if you violate, what happens to the mass matrix and stiffness matrix, we already demonstrated an example. As we then said that the mode shape is a relative displacement of the mass position in a given system. Now, I will take you forward to use this mode shape as an application of Maxwell-Betty's reciprocal theorem. Maxwell-Betty's reciprocal theorem has got a very great advantage in structural mechanics, saying that the force on a given system applied at one point giving displacement in the other node will be equivalent to the force applied at the other node displacement measured in a different node. I will explain this. I will use that concept for mode shape to understand and to explain how mode shapes can be used. Now, to carry forward this mode shape which is available as an eigenvector by solving the equation of motion as an eigenvalue and an eigenvector, I want to normalize this. Now, the question is, why do we have to normalize this? If you normalize the mode shape, there are advantages when you do the mathematical modeling, and also most importantly the physical advantage is you can use indirectly the Maxwell-Betty's reciprocal concept. See, it is very clear that Maxwell-Betty's reciprocal concept in mechanics can be used only for small displacements, whereas in this case the displacements are only quantified in relative value. You really do not know whether one means what, how much is the millimeter or centimeter, you do not know. So, one cannot really say whether the displacement is minimum or less within the elastic displacement of the system, we do not know that, but Maxwell-Betty's reciprocal concept can be applied here. Okay. To make that applicable, we have to essentially normalize these modes. So, then what is normalization or what is orthogonality? We need to have the modes orthogonal to each other. Okay. Let us see what is orthogonality. If phi is a mode shape, in my case it is half and 1, one can have it as 1 and 2 also. It is question of only multiplier out. Whatever the multiplier is taken out, there is no consequence, only the relative displacement as a consequence. Either you can say 1 as multiplier out and you can say this 1 and 2 and so on and so forth, does not make a difference, it is only the relative displacement between the 2 points. and phi 2 in this example is 1 and minus 1. You can always say minus 1 and 1, does not matter because it is relative, and we already know that for second mode there will be 1 0 crossing, for nth mode there will be n minus 1 0 crossing, which will enable you to really find what is the corresponding number of the frequency in a given multi-degree freedom system model. Now, put together in mathematics we call this as capital phi matrix, which can be written as half 1 minus 1 and minus 1, nothing but putting the vectors column wise and making a matrix, that is called eigenvector. Now, this is an mode shape matrix, each column represents the corresponding mode shapes. The moment I say phi I transpose phi j is equal to 1 for I equals j, equals 0 for I not equals j, then the modes are orthogonal. Now, let us first understand whether the available modes are orthogonal or not. If they are not orthogonal, then you can make them orthogonal. Okay. Once we understand that, then we will talk about what is the advantage of making them orthogonal. First, let us see are they really orthogonal or not. Let us check. Now, I want to check the orthogonality of the modes. So, phi 1. So, if I expand this, let us say phi 1 transpose phi 1 should be 1, phi 2 transpose phi 2 should be 1, phi 1 transpose phi 2 should be 0, phi 2 transpose phi 1 should be 0, because if an I and j are not equal, it should become 0. If I and j are equal, it should become unity. Let us apply this here. I want to find phi 1 matrix is a vector is given to me, which is half and 1. Phi 1 transpose is half and 1, because this is 2 by 1, 2 row and 1 column. It is going to be 1 row and 2 column, that is why I have transposed it. Let us find out phi 1 transpose phi 1. Let us see what happens to this. So, it is going to be half 1 multiplied by half 1. You can see this is 1 by 2, this is 2 by 1, there is a compatibility, therefore, you can multiply and you will get a unique value which is 1, okay, only one number. That value should be equal to identity or 1 if it is orthogonal. Okay. You can check this, which will be 1 plus 1 by 4, which will be 5 by 4, which is not equal to 1, is it not? Similarly, one can also try with phi 2 transpose phi 2. Which is 1 minus 1 of 1 minus 1, which is also not equal to 1. So, they are not orthogonal. These modes are therefore not orthogonal. Okay. I want to make them orthogonal. Now, let us borrow the mass matrix of this problem, which is 2m 0 0 m. The off diagonal terms are 0 because the degrees of freedom are measured at the point where the mass is lumped. The leading diagonal elements are always diagonally dominant, therefore, you can always invert this matrix if you wish so. Now, one can normalize these vectors, one can normalize the eigenvectors or otherwise called as mode shapes, with respect to either mass matrix or stiffness matrix. Let us try to normalize, with respect to mass matrix. Let us say M1 is a number which I now will get as phi 1 transpose M phi 1. So, let us expand this half 1 2m 0 0 m of half 1. You can see the compatibility 1 by 2, 2 by 2, 2 by 1 is compatible. You will get a unique value which is, let us say, M1. Can you find what is M1? First you will multiply these two, then post multiply this vector, you will get M1. 3 by 2 M. So, 1.5 M. Okay. Now, to normalize phi 1, divide phi 1 by root of 3 by 2 m, that is phi 1 star, which is normalized, will be root of 2 by 3 m of half and 1. Okay. Similarly, let us try to find M2. Let us find M2. Similarly, M2 is going to be phi 2 transpose M phi 2. This is a vector, this is a matrix, this is a vector, which will be 1 minus 1 2m 0 0 m 1 minus 1, which will give me a unique value which is m. So, divide phi 2 vector by root, okay. Therefore, phi 2 star, which is a normalized vector, will be 1 by root 3 m of 1 and minus 1. So, let us say I have normalized vectors which is this value and this value. Let us check, is it really satisfying the orthogonality condition or not. Since we have orthogonalized, since we have normalized phi 1 and phi 2 with respect to m, hence phi 1 transpose m phi 1 should become unity. Okay? Try. Phi 1, I can put a star here because we have used star there. So, you know the value. Can you give me what is this value? Okay. Similarly, 1 by root 3 m of 1 minus 1 2 m 0 0 m of 1 minus 1 1 by root 3 m, okay, will be 1. Now, let us check the cross product also. Let us check phi 1 transpose m phi 2. Let us see what happens to this, because it should become 0. Let us see. So, root of 2 by 3 m of half and 1 2 m 0 0 m 1 by root 3 m is it becoming 0? Because the m will get cancelled automatically, you will get 0. So, that is a check that phi 1 star and phi 2 star or the normalized vectors. So, as such when you solve an eigensolver problem, the vector what you get may not be normalized. Okay. So, you have got to normalize it with respect to m or respect to k. I will take up an example later that if you normalize with respect to m, what would be the advantage, and normalize with respect to k, what would be the advantage. Generally people prefer to normalize with mass matrix because the off diagonal elements in mass matrix are generally 0, okay, in a given problem. Therefore, the computation becomes less expensive. Okay. So, people prefer to normalize the matrix or the vector with respect to mass matrix because it becomes easy computationally. When you apply in the equation, it becomes more easy. We will talk about that slightly later. Now, the fundamental question is arising in mind is a vector I have obtained from the eigensolver, I have normalized it, fine. So, if I just multiply this with 2 over root 3 m or 1 over root 3 m, I will get a new vector. Still the relative displacement remains same. Okay. How I will physically now understand the advantage of normalizing it compared to that of non-orthogonal modes. Now, we will take the help of Maxwell-Betty's reciprocal law. So, you have a system which is a stick model of this like this. Let us say this is 2m and this is m, replaced by some spring, replaced by a spring. When I apply a force to the system in the lateral direction, I call this as P1, in the lateral direction. Then again a fundamental question comes in mind is, if I apply a force in the lateral direction, the springs are provided in the vertical direction. Okay, let me, how are they accounted for? These are not linear springs, they are bending stiffness. Okay, we are talking about EA by L for the springs. Okay. So, when the stick bends, they restore, therefore, the bending stiffness, because stiffness is a character related to restoration in a given system. Okay. So, if I have any model which restores the equilibrium position, then it is always a stiffness. It is not axial, it is bending. I have used EA by L here. If you look at the derivation later, what we did in the last class, we have used EA by L for our equations. When I push the model by a lateral force from the left to right as P1 applied to the node 1, this is node 1, let us say this is node 1, this is node 2. I am making it very clear, this is node, okay. This is mode. The mass is displaced, this is mode, okay. The first mode and the second mode. Let us say these are orthogonalized modes. Okay. Now, let us explain the advantage of orthogonality applied to dynamics here. Let us say I have a question. In this problem I have got only 2 modes because there are 2 degrees of freedom. If you have got n degrees of freedom, practically speaking n story building, because every story will have a mass and mass point will represent x1, therefore n story. Let us say 100 story building, I have 100 modes. One hypothetical way of looking at it is solve all the 100 modes and normalize them and have all 100 modes in pack ready. But I have a question here. Let us say if the load P1 applied at node 1 displace the system by phi 1 1, this notation is simple. The first indicates the node, the second indicates the mode. So, by that logic I can call this as phi 2 1. The first letter indicates the node, the second letter indicates the mode. Okay. Similarly, I can call this as phi 1 2, this as phi 2 2. Okay. These values are known to me. The question what I want to ask is, if I apply the force P1 at node 1, it displays the system in the first mode of vibration as phi 1 1, which is known to me. I wanted to know what is the effect of this force on the second mode, third mode, fourth mode, nth mode. I want to know. Maxwell-Betty's reciprocal theorem says, if I know the displacement offered by a deflected profile because of load applied at one node, it will be equivalent to the displacement caused by the force applied at same node but different mode. On the other hand, phi 2 1 and phi 1 2 should be equal. So, if I am able to establish that, I do not have to find the second mode at all. I got the first mode, I can keep on finding the displacements or response of the system for all the forces in all the modes. Okay, that is an advantage here. Maxwell-Betty's reciprocal theorem is applicable only when these modes are satisfying the normalization with respect to mass. Now, the question comes why? Because Maxwell-Betty's reciprocal theorem in statics is applied only for a force, but here we are not talking about the force. Okay? We are talking about the acceleration caused to the system which results in this vibration. So, my force here is m1 x1 double dot, that is my force actually. Okay? So, P1 is not the problem here, the P1 is not applicable here, it is m1 x1 double dot. So, I am applying an inertia force to the given system. Therefore, I must normalize the vector with respect to mass. Okay? I normalize the vector with respect to mass. When I do this, then deflection at mode 2 due to force applied at mode 1, all are mode only, no node. Okay. Deflection at mode 2 due to force applied at mode 1, same as the top. Deflection at mode 1 due to force applied at mode 2. Now, the argument comes here because Maxwell-Betty's reciprocal theorem is focused on a point of application which is the node in this problem. Okay. There are two parameters here, please do not get confused about this. There is an interpretation of Maxwell-Betty's law for dynamics. Okay. It is maybe a new perspective of understanding. Many textbooks may not agree with this statement, but this is a well known established fact when you talk about modal response parameters, which I will explain in a problem later in this in the same module end. So, there you will realize the advantage of this. Now, Maxwell-Betty's reciprocal theorem in statics has got two parameters varying. One is the point where you are applying the force, what we call as a node. Other is the deflected profile of the beam or the section, which is the mode. Now, here the explanation is only on the mode, okay, provided the modes are orthogonal and right here deflections are measured same node. Okay, that is very, very important. So, this gives me a great advantage of understanding the response of the system for forces in different modes. Now, here the force under context is not the lateral force, it is the inertia force. Okay, because we are talking about vibration. The deflection here is not the rotational or transformation deflection of the beam, but this displacement which is relative of the mass points in a given system. So, that is how we can interpret. Okay. Let us physically understand this statement, because it is very important to understand this statement. Now, what actually I am interested is the following. I have got a 2-degree freedom system model where the mass is lumped at 2m and m as shown in the figure. I have mathematically idealized the given frame with 2 springs and 2 mass as indicated here, and the whole structural system is now under vibration at 2 frequencies of omega 1 and omega 2. If at all they vibrated omega 1 and omega 2 under the given system, the shape of mass displacements relatively will look like this. Okay. Now, I am able to understand this once I have all the 2 modes plotted. If somebody asks me a question back again, what would be the deflected position of the mass m1 when the force is m2 x2 double dot? I do not have to look at the second mode, I can simply say it is going to be the same as the value at m1 x1 double dot. So, this will enable me to truncate the higher modes to the lower modes, which we call as modal truncation possibilities in higher modes of degrees of freedom. So, when I have got more modes to be represented in a given problem, I need not have to counter for all the modes, I can filter few modes and still get the same essence of representation from the few modes, provided these modes are all normalized. So, that is the catch here. So, we are extending the Maxwell-Bettis reciprocal rule and advocating it indirectly for a vibration problem, and there is a basic violation here which engineering community will definitely challenge. Maxwell-Bettis reciprocal law is applicable only when the deflection is small, but here we do not know whether they are small or large, they can quantify it. Okay? That is only a law which you are trying to. I am not saying that Maxwell-Bettis reciprocal theorem is applied to dynamics, I am not saying that. I am taking that advocacy and applying it for my understanding, because this will help me to truncate the higher modes in higher MDO problems later. Okay. Ideally speaking, I can have all the modes and all the frequencies, which is very difficult to find in certain cases. Okay. So, I can easily use only the lower maybe couple of modes or till 3, till 4, what we call modal truncation. When will you truncate the mode? We will talk about that later, but one can truncate the modes. You do not have to have all the mode shapes. Then you may ask me a worry, sir, there is a mode shape which is truncated, but unfortunately I want to know what is the displaced position of the mass at that node because of the force applied at mn xn double dot, because this mode is not available to me. You can get back and show that this will be as same as m1 x1 double dot at the nth mode. It is easy, relatively it will be same. So, that is the advantage what you have. This is a very interesting phenomena for design, because people are talking about the maximum tip displacement in design. This phenomena can be easily applied for that. Okay. That is the advantage what we are talking about, orthogonality of modes. Now, we will move on to multi-degree freedom system models, where I really wanted to find omega n's and phi n's by some numerical methods, because as I go higher and higher, in this example you saw you have been solving a quadratic equation. So, if you go for a third degree, you will be solving a cubic equation, and cubic equation solution will have at least one value to be assumed by inspection. Okay. It is very easy in a mathematics saying that x cube minus 3x square plus 4x minus 5, you can easily by inspection find x is minus 1 as a root, but here we are talking about a number of 3.464, 4.948, it is very difficult to find them by inspection. So, there should be some numerical tools available in the literature which will help me easily to find out omegas and phi's for n degrees of freedom model other than eigenvalues and eigenvectors. Number 1. Number 2, eigenvalue and eigenvectors can be applied, or eigensolver can be applied to a problem when the mass and stiffness matrix, because it is k minus omega square m determinant. When the mass and stiffness matrix are diagonally dominant and the convergence is sure. But in certain cases your mass and stiffness matrix may not be diagonally dominant. Then in that case this will lead to a very catastrophic solution mathematically. You will not be able to find the solution of all the modes, whereas numerical methods can give you this step by step. So, therefore, we are now attempting to find an approximate solution, not accurate, because accurate is of course only this approximate solution, but I will show you in some examples where this and all numerical methods we will attempt here will give you exactly the same answer. Okay, it will give you exactly third digit answer will be same. Therefore, you can appreciate how these numerical methods are so intrinsically defined, therefore, they will have no error at all, and they are very easy to follow, and very interestingly many of the textbooks and authors do not illustrate them with many examples of our choice. They will take up a same spring mass problem and establish in all, which I will do variety of problems for you to understand one by one all the methods thoroughly. Then I will take up couple of problems and solve the same problem by all the methods, and I will show you that the answers are converging by any method you want, and all of them are easily programmable also. On the other hand, if you really have a structural form of your choice for research, you can pick up any one method, write the coding in MATLAB or in C, any language, and you can find omega and phi, which is the vital characteristic of any dynamic system for which standard solution is not available from a software. Because to find the standard solution for this problem from the software, you have got to mathematically model this problem first in software, where you are not comfortable with. But you can be comfortable writing the coding for the numerical methods easily, because it is step by step algorithm, very easy to understand. There are codes available also. In fact, I can give you all the C codes and MATLAB codes here in the course itself. Just simply plug in, substitute the values of m, k, etc. In minutes you will get your omega and phi automatically as number of omegas and phi's. All omegas and all phi's you will get, whereas in certain cases it will be difficult. But there is a problem in these methods. The convergence of the method, because they are iterative in nature, it is only dependent on the observation or the initial assumption what you make. That initial assumption needs experience. So, this is where people cannot apply this generic to all problems. Therefore, software do not follow this method, because that initial assumption need to be given by the interpreter, who is the user of the software, who has absolutely no idea what dynamics is all about. Therefore, he cannot. Unfortunately, people who know about dynamics also cannot give those values, because they are not solved by the authors in the textbooks. Therefore, they are really fed up. If you have a new structural form where you do not have the skill of numerically modeling them, you cannot find omega and phi so easily using a computer or using a software. You cannot also solve using classical eigensolver, because there are n numbers, there may be a problem here. Then where will you land? Many of the research problems stop here, because the structural form taken by the candidate or the researcher is not solvable for finding the fundamental characteristics of dynamics problem. Therefore, they stop there, they do not take it forward, or they try to find out approximately wrong solutions and they go with the design and the whole design can become absolutely wrong. So, numerical methods are very important. Generally, people see numerical methods as a sideline for the original mathematics, which is not correct, because in this case I am re-insisting the numerical methods will give you exactly the same answer as that of the classical analytical technique. There are three methods: experimental, analytical and numerical. Experimental is what you conduct experiments and get the value. Analytical is using a code ABCs and get the value. Numerical is model it in FEM and get the value. Okay. Analytical anyway I have demonstrated for 2, I will not do it for 2 more, but I will do all the problems in numerical, make you to understand. Experimentally omega and phi cannot be obtained, only damping can be obtained. Okay. So, now we will resolve and we will all agree that numerical methods are interesting for multi-degree freedom system models. So, let us talk about numerical methods. Only to find omega n and phi n. Okay, I put a bracket like this because they are couples, they are married. The foremost method which comes in mind is Dunker-Lee. Dunker-Lee has given a method for estimating the fundamental frequency omega 1. He did it in 1895. That is the beauty of this method. It is more than 100 years old. So, imagine on those days matrix method was not available in engineering, computers were not there, calculators were not there, only slide rules were there. Probably I do not know 1895 whether even slide rules were there or not. Okay. He has given an algorithm. We will solve the problem using this algorithm. We will pick up another numerical method using computer technique and solve the problem. The answer exactly will be same. Okay, it is exactly same. So, in fact, before we do this method, I think we should stand salute to this fellow because he has given a wonderful technique which is quick and simple from the basics. You will never make a mistake. So, in any problem you have, if you are able to work out Dunker-Lee's fundamental frequency, most of a design is done for the form. Okay. So, we must know what is my fundamental frequency. Okay. So, we will see how this method is developed by Dunker-Lee. This method is applicable to discrete systems only. If the mass is continuous, you cannot apply this system, you have to have a lumped mass. He said simply that 1 by omega square is 1 by omega 1 square, 1 by omega 2 square, 1 by omega n square. N here does not mean natural, n is the nth degree. Okay. Let k 1 be the spring constant. We know that k 1 is 1 by delta 1 1, where delta 1 1 etc. are called flexibility coefficients, because stiffness and flexibility are inverse of each other. So, omega square or omega 1 square is k by m or k 1 by m 1, and k 1 is 1 by delta 1 1. Therefore, this is 1 by delta 1 1 m. Similarly, omega 2 square will be 1 by delta 2 2 m. Omega n square will be 1 by delta n n m n. I call all these equations as equation 2. Substituting 2 in 1, we get one by omega square will be delta 1 1 m 1, delta 2 2 m 2, delta n n m. That is sum of delta I m I varies 1 to n, where n is the number of degrees of freedom I will call this as equation 3. Let us physically understand what Dunkerley has proposed. Dunkerley has proposed to find out or help you to find out only one frequency, which will have a contribution from all frequencies. Okay. Now, you know all the mass, because mass is one of the essential characteristic of a given dynamic system. If the mass is not there, inertia force is not there, therefore, you do not have to do dynamic analysis, we already said that. So, in equation 3, by some method, hook or crook, if I know how to work out delta II, I will get omega. Okay. So, I am interested in knowing how to work out delta II. If I know how to find delta II for a given system, I know m1, m2, mn, I can easily find omega square, take a root, I get omega. Okay. So, in this factor, he has not focused on deriving stiffness matrix at all. He is helping us to find out the influence coefficient. Okay. Let us try to find or understand an algorithm how to get delta II or delta 1, 1, 2, 2, etc. for a given problem. So, to understand this, I must take a problem and demonstrate how to get delta 1, 1, 2, 2, etc. Then only I will be able to solve this. Let us take one simple example. So, just for a self check, you should be able to write the equation of motion for this in a matrix form using Newton's principle as well as using energy method. You can always try. What Dunkerley proposes is very simple. He is interested in finding out the deflection for unit force. Okay. That is how stiffness will become deflection if the force is unity, because stiffness is force per unit displacement, but if the force becomes unity, the displacement will become stiffness directly, which is inversely connected. Okay. So, what he did is you give unit force to the system, and of course, the system continues unit force at this point at x1. So, to find delta 1 1, let us mark the segments as A, B, C and D. Segment AB has got two springs in parallel. I can always find K equivalent of this segment as simply the sum of these two, which is 4K. So, I will replace this with single spring, which is 4K. Similarly, segment BC has got two springs in series. I can easily find the K equivalent . To K by 3. For the segment CD, the equivalent spring, I will replace the single spring, which is 2K by 3, and this will have a single spring which is simply 4K. So, K equivalent is straight away equal to 4K. So, we know K is force by displacement, force is unity in this case, displacement is the coefficient, K is K equivalent of the respective sector. So, if I am giving unit displacement at the first sector, I will get delta 1 1, which is nothing but 1 by k equivalent of the first sector, which is 1 by 4 k. Now, I want to find delta 2 2, because in this equation if you see omega 1 by omega square is equal to sum of delta I mi. So, I want 1 1 2 2 3 3. I do not want off diagonal elements in this matrix. I want only the elements along the diagonal 1 1 2 2 3 3 and so on. Now, to get 2 2, I must get unit force here as I did for 1. The moment I give unit force here, I want k equivalent of the remaining part of the problem. So, now I have got 2 springs 4k and 2k by 3 in series. So, k equivalent for the segment or sector BC to find delta 2 2. So, now the system is 1, but this is going to be k equivalent nu. This k equivalent will be 1 by 4k plus 1 by 2k by 3. So, I put it like this here, which is 7 by 4k, which is 4k by 7. Okay? And delta 2 2, as you see from this equation, is the inverse of 1 by k equivalent. I get 7 by 4k. Now, I want to find delta 3 3. Now, to find delta 3 3, apply this concept for the entire segment ABCD. So, I have got 3 springs 1, 2 and 3 in series. Therefore, 1 by k equivalent of the segment ABCD is 1 by 4k plus 1 by 3k by 2 plus 1 by 4k. It's 3 by 2k, is it not? So, 1 by k equivalent is 8 by 4k. Therefore, delta 3 3 will be 8 by 4k. So, 1 by omega square will be sum of delta I mi I 1 to 3 in this problem. So, all are m, therefore, m is taken out. Delta 1 1 is 1 by 4k plus delta 2 2 is 7 by 4k plus 8 by 4k, which is 16 m by 4k, which is 4 m by k. So, omega can be found out as root of k by 4 m, which can be the value. So, Dunkerley has given the fundamental frequency of vibration of the system, which is 3 degree, in just simple steps like this. Now, Dunkerley has got a very major disadvantage. It idealizes the spring as an equivalent system. It does not give me the mode shape corresponding to the frequency. It will give you only the frequency, not the mode shape. Therefore, this method is considered to be approximate technique of finding the frequency. Now, one will be interested to know what happens to my off diagonal elements in my delta matrix, because it is talking only about the diagonal elements 1 1 2 2 and 3 3. What happens to my remaining elements? We will talk about that slightly later in the next example. So, the home assignment is very simple. You must be able to derive the equation of motion for the given problem, not from equivalent system, but from the regular system itself using energy method and Newton's method, and you must compare and you must get the same equations of motion for this. You can also solve this using a classical eigensolver problem and get omega 1 and see is it coming to be 0.5 k by m or not. These two are take home assignments for you for your self interest, but I will proceed forward in the next method that will make use of this and proceed forward for other numerical methods. Any doubt or any questions? Okay, thank you.